pessimist doesn't look at that and say, oh, that's sugar. That's an extra 5 pounds on my hips. Okay. That's probably what a pessimist is looking at. Okay. Or that is a stomach ache in an hour or 5 minutes whenever I finish the whole pie. Okay. What does the optimist see? It looks good. It looks tasty. That's awesome. Give me some of that. Why are you just showing me a picture at lunchtime of dessert instead of bringing in an actual pie? Okay? Just because it's fun. What does the scientist see? So a scientist may go through and start to process the ingredients, but why do they care about the ingredients? What do you got?
So they know the chemical properties and how it reacts to other chemicals and or just whatever.
Why do we care, though? Why do we care?
To replicate the pie.
Step more than that, but yes. So replicating is a possibility. What do you have as a suggestion?
Similar, the parts make the whole. So when you know what everything's in it, you know what it really is.
Okay, but why do I want to know that? So there's a philosophical sense behind that that works.
You can tweak it to make it sound different.
There's a good answer. A scientist looks at it and says, that looks pretty good. I can do it better. So they're going to go through and look at each of the individual pieces behind it and say, you use granulated sugar, I'm going to use turbinado sugar because it has better flavor. So that when I get to my pie and I make it, everybody's going to eat my pie and say, your pie sucks and my pie is the best. You may say, well, isn't that kind of egotistical? Yes. That is exceptionally egotistical. Okay? And whether it's nice or not, science and scientists tend to be very egotistical. Okay? You kind of have to be to get through it. Okay? So we will encounter lots of things through the semester. We're like, well, why do I have to learn this and that? Don't they mean the same thing? Yes. But the person that defined this and the person that defined that both had a lot of power and a lot of money. So when it came to the situation of, oh, this and that are the same thing, well, my that is more important than your this, so we need to talk about my that. Well, no, my this is more important than your that, so we need to talk about my this. And what ends up happening? You build two classes of people that both then have to communicate with each other. But to communicate with each other, what do they then have to be able to do? Convert between their individual languages, which then makes your life a living hell, because you are now responsible for dealing with all of those conversions and being able to understand how and why we do that. Okay? This is something we do on an everyday kind of system. For instance, how do we measure length? Inches and feet, really? Is that how the world measures length? No, the world measures it using a metric system. And yes, we measure it with a unit system. Okay? But we could use inches and feet and miles, but most of the world doesn't. Okay? Why do we not all agree? Because the U.S. has a lot of power, and the rest of the world didn't have enough power to convince the U.S. to change. We're now so ingrained into those individual systems that the odds that we will ever change, slim to none. Okay? Unless one or the other is entirely wiped out, and we start from scratch. Okay? Which, as much as I'd like one system, I don't want to go that far. Okay? So we have to work within that system and those kind of constraints. We get these kind of battles, and that's where our science builds from. Okay? So there is an inherent understanding behind it, but a lot of it comes from, I want to understand this so that I can do it better. Okay? I have something I can contribute to making this system better. Kind of make sense? Okay. So the other big topic that pops up is the scientific method. Okay? And really our goal is to learn something new with kind of the intent of making something better so that everybody remembers us and has to remember our names for infinity. Okay? So if we look at the scientific method, we can break it down into individual parts because we need an organization behind how we process this information. Okay? So you've probably heard of at least bits and pieces of the scientific method. And I'll be kind of mean and start you off. The very first part of our scientific method is observation. What other parts are there? Deduction works, theorize works. Our big term is hypothesis. Okay, we make an observation, the apple falls from the tree, something must have caused that apple to fall from the tree, gravity, poof, no. Okay, but kind of that level. We're coming up with an explanation for the observation. Okay, and then someone shouted out another answer. How do we then test our explanation? That's when we go to an experiment. Then what happens? Okay, a conclusion, recording the results. Theory, okay, influencing people. Okay, and that's typically how this is taught, and I would argue that is wrong. That's not true. What actually happens is failure. Okay? We don't succeed. Our hypothesis was ultimately and inherently wrong, and our experiment did nothing to match the hypothesis. Okay? And this is the hardest part, because science hits failure 90 to 99% of the time. But what scientists do with their egotistical brains is say, well, I can get through that failure. I'm going to change my hypothesis. But now I have a new hypothesis. What has to happen? New experiment. And then what happens?
More failure.
More failure. Okay? Scientists spend their careers cycling through failure. Okay? And you talk to some of the really famous scientists, okay, well, how did you come up with, this grand, awesome theory? How could you possibly do it? Oh, you must be the most brilliant, amazing person. And the ones that have at least some grain of self-respect acknowledge and say, well, no, I just failed 99% of the time. And the one time that I succeeded was that one time that everybody saw, because the other 99 times I shuffled under the rug and no one saw that. Okay? But that one time was such an awesome feeling of the world saying, you are brilliant. They're like, I'm going to keep doing this. Okay? And they go back to science and go back to trying to discover something else or create something else. Okay? So what we are ultimately learning to do in this class, as unfortunate as it may sound, we are learning to fail. That is our goal coming into this class.
So
Okay?
we fail in the class, we pass, right?
But we need to fail at the correct time. When is the correct time to fail? When you're practicing. When are you practicing for this class? Probably any time you answer a question. How many questions have I asked already so far this class period? A lot. Some of those answers were good or directions that I wanted to go. Some of those questions or answers were directions I didn't want to go with the class. Okay? So those answers were failures. Did anybody get out and leave as soon as they failed? Good job. You're scientists. Okay? We're dealing with that failure now, okay, so that we can work through our homework questions and advance and process and learn from that failure till eventually we can succeed. So when I want you to fail is in this classroom. When I ask a question, you can feel free to shout it out. If you want to raise your hand, that's fine too. I'll try and ignore people shouting and point at you if you've been doing it for long enough. Okay, or you can just shout it out. I'm fine with that. Okay? The idea is to get the idea of juices flowing and think about what's happening and how we're processing it and try and get it put together. Kind of make sense? And if we're really lucky, at the end of this class, we may end up with not a scientific theory or a natural law, okay, which is where most science leads to, but a passing grade. Okay? And ideally, I don't even want you to pass. I want you all to be in that A category. Okay? You won't all be there, unfortunately, but that's what we're working for. Okay? That's what I'm here to help you with. That's what you need to help yourself do as well. Make sense? So everybody excited to fail? That was encouraging. Okay. Most of our natural laws are kind of disappearing because, well, enough people have been studying them for long enough that our natural laws have kind of been discovered, and we're really just kind of working within scientific theory. Okay. Theory isn't, I think someone's going to walk through the door. Okay. Theory is testing it, and retesting it, and retesting it. When someone comes through with an observation, hypothesis, an experiment that they decide was successful and that they decide supported their hypothesis and they say, this is my theory, right? That doesn't make it a scientific theory. What makes it a scientific theory is thousands of other scientists go back and say, your observation was wrong, thereby everything afterwards was wrong. We're not listening to you anymore. Your hypothesis was wrong, but your observation was right. Fix your hypothesis. There's this iterative process that goes into a scientific theory. It doesn't just pop out of nowhere. One person just says, there it is, and we now accept it. It goes through many iterations of proof or attempting to prove. Because ultimately, theories we can't prove. We just provide enough evidence that really suggests no other option is available. That's what we're working with. Okay? But we need that experimental proof to push us to that theory. Fun stuff. Maybe. What is chemistry's role in science? Okay. Well, we really have the mathematicians and the physicists on one side of our bridge. The mathematicians, great guys and girls, can be a little loopy sometimes. They're usually so bogged down in the mathematics that they really don't care about the real world. They're just making numbers up and just doing weird stuff. Okay? One of the worst days for mathematicians is when a physicist comes along and says, hey, that little thing you just did, that explains this. Because then the mathematician goes, well, now my stuff had some use. Well, that sucks. I got to go back to the drawing board and find something else to work with. Okay? My parents are mathematicians. It's okay. That didn't even have to be true, but it's close enough. Okay? Physicists are really trying to understand at a very deep, deep level what's happening at either atomic levels or at massive ends of the scale, not subatomic, the other end, really big stuff. Okay? And they're using mathematics to help kind of explain that. Okay? We then get at the other end biology and other stuff kind of being engineering. And I'm sure we've got lots of engineers in here. Engineers like to say they're the bridge. That's a load of nonsense. Okay? Engineers aren't a bridge. They're building the bridge maybe, but they aren't the bridge. Okay? Engineers are on the application side of it. Okay? Biologists are on the application side of it. Okay? So you get the physicists and the mathematicians coming up with these crazy, oh, well, we can totally do this. And the biologists and the engineers being like, no, I don't understand what the hell you're talking about. That number, that doesn't exist. That doesn't make sense. The chemist's role is to kind of get in between and to massage some of the mathematics and the physics and turn it into something that we can relate to, something we can work with, so that the engineers and the biologists can actually explain what they're seeing at a larger scale. So we're really starting at so infinitesimally small with mathematics that it doesn't exist. And we start moving up and start getting into kind of larger aspects, but still math-heavy. We then get an interpretation of that math-heavy stuff into real-world things that we can grab and hold. That then transfers out to the biologists, engineers, and I'm sure other people. It's just, there's my grasp of how many different scientists there are that can then manipulate and work with that. Okay? Even within chemistry, we have subdivisions. Okay? People are going to argue all over the place, but let's just say there's 4. You get organic chemistry, you get biochemistry, you get inorganic chemistry, and you get physical chemistry. Okay? Which of those are you in?
Physical, inorganic.
Well, we really don't learn anything specific to organic chemistry. It pops in every so often. Biochem, I don't think we learn anything from biochem. Inorganic, we do a significant portion of inorganic chemistry, and we do a significant portion on physical chemistry. So really, what are you expecting to learn?
Chemistry.
All of them. Okay? This isn't one of those sections. This is all of them. When you move into general chemistry, it's all of them in more detail with some more physical stuff tossed in there. Okay? The only time that you start to branch out and become specific is when you achieve your second year of chemistry, and that's when you first encounter organic chemistry. Okay? And if you know anything about chemistry, that's the one that's coolest. The rest of them are just confusing and just weird. The organic chemistry actually deals with things that we can work with and have fun with and we can see and we can manipulate, and it's cool. Okay? Biochemistry is biologists attempting to sound cool by calling it chemistry in it. Okay? They do some cool stuff, but really, what is biochemistry? Really hard organic chemistry. That's it. Okay? Plants and animals, I would argue, is biology. Too far. But not a bad guess. Inorganic is everything that wasn't organic. Okay? Which you might laugh and go, oh, that's kind of a funny definition. That's actually kind of it. Okay? Most of inorganic chemistry tends to settle in the middle, known as our transition elements. Okay? Studying what those metals can do and how they interact. Physical chemistry is now looking at the subatomic level. How do all of our atoms, electrons, protons, and neutrons, and quarks, and subquarks, and thermodynamics, and all of that stuff interact to make everything else? So the physical is like you stepped 1 foot onto the bridge away from the mathematics and physics. Okay? The organic is like 1 foot away from the biology and other stuff. Okay? The inorganic, I don't know, they're somewhere in there. Okay? So we've got those different fields. You're expected to pick up bits and pieces from all of them. Okay? One of the things that is nice is that we do have kind of a lot of overlap between them. They all involve looking at periodic table. Cool. So if we can interpret the periodic table, that applies to every single one. Okay? They all apply to chemical reactions. So we can learn something about chemical reactions and then manipulate that back in. They all rely on conversion factors. So if we can learn how to convert different units, we've got that set up. So what we're really trying to look at is the big picture pieces that somehow translate a little bit into each one. That's what this class is trying to do. Okay? Perfectly easy. Not at all. Okay? So here's where we're going to start skipping around. We're going to skip into chapter 3 for a little bit. Okay? When we're looking at chapter 3, it's looking at kind of the broad picture of matter and the different compositions within it. There's two big terms that come out of this, because we're trying to now bring observation into this. We get qualitative and quantitative. What does qualitative mean? What's that? No, it actually doesn't have to do anything with the quality.
What's inside or what's present?
Can we make a qualitative observation of the picture? I don't know which one it is either. Okay. There's a lamb or a sheep. Does anyone want to challenge that?
Lamb.
I'd say there's 2 lamb or sheep, right? There's 2. Okay, but our qualitative is we have a lamb or lambs. Okay. What else would be a qualitative observation? They're outside. It's daytime, afternoon. Okay. They're white. They look furry. They're under a tree. Okay. Those are our qualitative observations. They're quick kind of snap judgments about just seeing what's there, using our eyes, if we were actually there, using our nose, okay, using our tactile response. Okay. Fun thing with qualitative observations is that if I wanted to tell somebody some more information about that, okay, like maybe the weight of that sheep. Sheep? Sheep? The weight of one of those sheep. Could I do that with a qualitative observation? No.
Isn't quantitative
Okay.
everything that's like measurements and numbers?
To get a measurement of how much that sheep weighs, I need an instrument. I need something else to measure. That's now my quantitative observation. My quantitative is bringing in the numerics. And as we'll continue to see throughout this semester, my probably least favorite part of chemistry is dealing with the numbers. But we could now say, well, there's 2 sheep. Sheeps. Shopes. In this picture. Okay? We could say one weighed Anybody know how much a sheep weighs? 40, really? 48 seemed kind of light. 48 pounds. Okay. So we've got some quantitative information. Which of those is more relevant? Depends on where we're going with it. Okay. If I tell the sweater manufacturer that I have a 48-pound sheep, like, okay, what do you want me to do with that information? How much wool is part of that? Okay. Is it soft wool? Or is your 48-pound sheep covered in glue? Because then I don't care about your 48-pound sheep because I can't use that wool. So it's really going to depend on who you're talking. You talk to the butcher and you say, I've got a 48-pound sheep. They're like, okay. That means I can turn that into 5 meals. It's a pretty big meal, but.
The quantitative is more specifics then?
The qualitative is still specific to that system. It's just not a measured value. And so it again comes down to who you're trying to give that information to. What are they going to use it for? Well, but qualitative is just as useful.
Okay.
Okay? So we can't say one is more useful than the other. They're different. Okay? Which side of the quarter is more important?
Who's to say?
Yeah. It's arbitrary on which side is more important. Okay? The side that tells you it's worth 25 cents. In which case you probably didn't care anyway. You're like, 25 cents. Okay. So it depends on our situation, on what we're working with, which one we're going to look at. Which one do you think came first as far as science was involved? Probably the qualitative. Okay? Because it's what we can see and feel. What is 70 to 80% of life? Water, H2O. Okay, so this is kind of neat. What's the interesting feature about water that is pretty unique as far as our natural habitat on Earth goes? When I physically observe water, what do I see? I see solid, I see liquid, and I can sort of see gas. Okay? I have ways of now qualitatively organizing the matter that I have around me. I have solids, liquids, and gases. What else could I qualitatively analyze about those phases? So we're looking at solid, liquid, and gas. So the temperature at which we're at to get to that phase, that's an interesting observation. Color is an interesting observation as well, though color becomes a bit dicey because what color is that water? Clear. What color is the gas? Clear. Okay. What color is solid ice?
Depends.
It's clear. Why does it look white as snow? Trapped air. Okay. So that material is still pretty much clear or colorless all the way through. So yes, color can be helpful, but it's not the easiest one to work with. Okay. We could look at shape. Okay. Does it hold its shape? Okay. If I dropped, well, I've got to ignore temperature, but if we just had ice and I put it on the table, what's going to happen to the ice? Okay, we ignore temperature. Temperature's not an effect. Put the ice there. What happens to it? Nothing. It just sits there. Okay, well, that's exciting. What happens if I take liquid water and I pour it on the table? It spreads and moves. What happens if I take gaseous water and put it on the table? Really spreads. Okay, so our shapes end up changing and have different options available to them depending on the phases. What about volume? Does the volume of the solid change? Put it on the table. No. What if we push on it when it moves? Okay. No, the volume doesn't really change. How about liquids?
Informs.
Liquid water. So it deforms. Did the volume change? Okay. So if I push down on one part of the water and the water moves up the other side, Well, I lost volume on one part, but I gained it on the other. The net is the volume didn't change. What happens with gas? It can be compressed significantly, okay, or expanded significantly. So our volume is highly variable for a gas. Okay? How about compressibility? Kind of ties back to our volume. The volume doesn't change. Can you compress it? Compress means to squeeze and ultimately shrink it. The volume doesn't change. Can you cause something to shrink? No. Okay. So the compressibility for solids and liquids? Virtually nothing. How about for gases? Yeah. There's a lot we can do to compress those down. So what we can also do is go through and attempt to interpret this, okay, with a drawing. If I was going to say this was my water molecule, and I'm looking at a solid, well, I need more water molecules. Where should I draw the next water molecule? Why immediately next to it?
In that solid state, like that, all of the like particles are going to be tightly closer together, just because they're a lot more condensed.
What does that mean about our compressibility? To compress, we have to lose space. Is there any space between my particles? No. So when we said solids aren't compressible, why are they not compressible? There's no space. Okay? What happens as we move to a liquid? I get a little bit more space, but for the most part, because we again said our liquid general observation, there's very little space there. Tiny, tiny space. What happens when I move to a gas? Well, then the other one's, somewhere over here. Okay? We have this massive space. So we can compress that. We can compress that because there's a bunch of space there that isn't occupied by anything. So we're trying to make these qualitative observations about the phases of matter that we've got. Okay? When we look at matter, we can really subdivide it into two categories. We have mixtures and pure substances. Okay? Mixtures are spatially linked. Okay? This room, with all of you in it, would be a mixture of people. Okay? To be a pure substance, we'd all have to be chemically linked. Okay? That means we all have to somehow form into each other and become a massive human blob. Okay? That would be the chemical linkage. Okay? So we have the same kind of thing happening with atoms and elements. Okay? A mixture is just saying I have a bunch of things that are all near each other, but they aren't physically holding on to each other. The pure substance, they're holding on to each other. And every single thing in there is holding on to the exact same type of thing in the other systems. Okay? And of course, it wouldn't be chemistry if it didn't get more difficult. We, of course, have to subdivide those down into two further categories. In the mixtures, we have heterogeneous mixtures and we have homogeneous mixtures. The heterogeneous has a visible separation. The homogeneous has no visible separation. Okay, well, is that inherently obvious? Really? Something that's inherently obvious? Salt water. Homogeneous, heterogeneous. Ocean water. Why is it hetero? We could reference the sand in the water, but if I just said ocean water, how do you know there's sand floating in it? Okay. We could pull out fish, okay, if we just said the ocean. Okay, the ocean would be an example of a heterogeneous system. Ocean water could match in either, depending on what we're sliding into it. Okay? The visible separation, I think, is a difficult one to associate. So what I would actually subdivide this into is actually calling the visible separation multiple and the homogeneous being single. Multiple and single what?
Mixtures. Elements.
What did we just talk about?
Separation.
Phases. A heterogeneous mixture is one where there are multiple phases present. A homogeneous one is one there is only a single phase present. Okay. Sometimes that's obvious, sometimes that's not. Fog. What is fog? Why are you saying hetero?
Okay, I don't necessarily know what fog is either, but I just feel like it's something having to do with moisture and that kind of stuff.
Okay, someone else want to jump in on that?
Air and water.
Yeah, fog is a mixture of air and water. Okay. Well, there's water in the atmosphere now. Why do we not see fog? It does have to do with temperature. What is happening with our temperature? Ultimately, pressure, too. Because right now, it's a homogeneous mixture of air and water. To get fog, what has to happen?
Isn't the earth warmer than the air that's like around it?
You may be getting too far into the meteorology side of that for me to be able to answer that question appropriately. You might very well be right. What is happening when we see fog? What are we seeing? What part of water? Water condensing on air. So this is the next part, is when we say water, what are we referencing? The solid, the liquid, or the gas? That's really hard, because water can be any one of those. Okay. When we're saying fog, what we are saying is liquid water. And air is gas. Okay. So when fog comes into existence and we see it, the conditions have changed such that the water that was a gas has become a liquid. By becoming a liquid, what does it do to light? It reflects the light differently, and we end up seeing a sheen or that fog appearance. We can't see through it anymore. The light gets reflected in all sorts of different directions. Okay? It's getting reflected because there's a different phase there. If there was no different phase, what happens? You see through it, it's a homogeneous mixture all the way through. Neat. Okay, what about on the other side? Pure substances, chemically linked. Okay. Those subdivide out into two categories. Compounds. Compounds are at least two elements. Okay. The other one is, well, just elements. If one is at least two, the other one's going to be one. That's it. Okay, that's our differentiation there. Okay. How many of you have had a chemistry class before? Okay, so the other half that haven't had a chemistry class, officially, you don't know what an element is. So we just defined an element with an element. That's a pretty awful thing to do. Okay, what are we saying when we're referencing elements? So our periodic table, it's the smallest, which we'll debunk here in a little bit. Okay, smallest particle that defines an element or defines a structure. Okay. If I then combine those pieces with each other, I can make compounds, okay, by combining multiple elements. Kind of make sense? Questions? Okay. So, if we look at our elements, we can categorize those, because of course we can't stop categorizing, we just got to keep categorizing until we're done. Okay. Our elements are all scattered across the periodic table. We've got metals, metalloids, and nonmetals. Let's skip the metalloids for the minute. We have metals and we have... Okay. This is a really creative definition here, right? I have something that is a metal, and then I have something that is not a metal. Okay? That is what we're doing. Okay? We're trying to make them as opposite as possible. If we go through and compare these, the metals versus the nonmetals, okay, we've got a list of attributes. Which of those applies to the metals? Which applies to the nonmetals?
Metals is going to be the left-hand side, and then the non-metals is going to be the
Okay, how'd you pull that one off?
well, I read that textbook last night, so
That works.
remember that it said most solids are going to be up in the metal section, and that it's going to be valuable.
We're referencing our elements, right? Do we have something that summarizes our elements? Readily available in every chemistry class, on every exam. Some people even have it in their cell phone as a little app. Oh yeah, we have a periodic table. Does the periodic table tell us anything about solids or gases? Yeah, because we got this nifty little key down here. It said solids, liquids, and gases. Okay. So we see a whole bunch of them. Most of the black ones are on the left. Okay. And then we got some reds and blues on the right. Okay. We get the most variability on the right. Notice that there's also this heavy dark black line zigzagging through the middle there. What do you think that line might be presenting? A separation between what? Metals and nonmetals. Okay, so we have a differentiation there. It is there. So now the question becomes, well, which is which? Okay. To do that, that's where we have to look at the rest of our properties and try and classify and find them all out. Does anybody know other properties of metals that are up here that you're like, yep, I knew that one? Anybody have any silver jewelry? No, nobody has silver jewelry. Anybody use a fork or a spoon today? What are those made out of? And I'm hoping I don't get plastic.
Sterling silver.
Sterling silver, stainless steel. Okay, both of those are examples of metals. Okay, stainless steel is a bit of a weird one because that's not an element. That is a mixture of elements. One of those elements in that mixture happens to be iron. Okay, so we could look for iron on the periodic table. And of course, that's a fun one because what's the symbol for iron? Fe. You didn't know that? That's fine. You will by the end of the class. Okay, Fe, that's our symbol for iron. I said silver was another option. What's the symbol for silver? Kind of a jerk picked symbols that didn't make any sense. Ag. Where do we see Fe and Ag? With respect to our staircase. The left. Okay. Is there anything we would immediately say that's not a metal? Right? Or I can't do that. Helium could work. Oxygen. Do we know the symbols for helium or oxygen? He is helium. There it is, upper right. Oxygen. A little bit lower. There it is. Okay. Where are oxygen and helium, being nonmetals? On the right of the staircase. Guess where the nonmetals are? Right of the staircase. The metals? Left of the staircase. What is a metalloid? Okay. It's a mix between. Where do you expect to find a mix between? Probably on the staircase. Okay. So we now have a rough classification on where to find our metals, our nonmetals, and our metalloids. The metalloids are a bit irritating because is it every single one along the staircase? No. It kind of jumps around a little bit, which means I don't ever ask that question. And we'll keep our focus on metals and nonmetals. If we take a look at the images up at the top, what do you think? Metals, nonmetals, metalloids? Maybe this will help. What do you think these ones would be? Those would all be it's kind of challenging, isn't it? Guess what the first one is? Metals. Those are all our metals. So our metals, the luster there is referencing shiny. Okay. All of those are fairly shiny. Almost all of our metals are shiny. Think back to that stainless steel or your silver or your gold. Okay. Those are all examples of metals. They all have that kind of shine associated with them. Oh, don't screw it now. Next one. Nonmetals. We don't really have any shine. Okay? We're seeing some bright light coming out of there. That one's a bit weird. That's actually an interesting observation, which we'll talk about again later. Okay? On our far right, we've got carbon, okay, woven together with a bunch of other materials. Okay? But those don't have a shine. Those are primarily dull. They're also brittle. Okay? They don't conduct electricity or heat very well. And then the last ones, well, if we had metals and nonmetals, presumably we dropped in the metalloids. What makes the metalloids very difficult to assess?
Because of those shine.
They share properties of both the metals and the nonmetals. Really, the only way we'd be able to tell a given sample was a metalloid is by testing all of those visual, or all of those aspects. How many of those aspects do you think you could test for right now? Solid, I agree, because you can see that. Looks like a solid. Right, the shine, conductivity. You can look at that and tell me it conducts electricity? Okay. We really only get 2. So we've got all these observations that define metal and nonmetal, and of those, we really only have access to maybe 2 of them to help us interpret between them. So that's not an easy task to just look at them. I don't expect you to do that. It's just trying to get you to think about it. Make sense? Which then gets us to our periodic table, and that link or that direction, Canvas helpful files, will exist in a little bit. I just forgot about it. Okay. We have the periodic table. It is our language. Okay. It is the alphabet with which chemists work. Okay. And if we think about our language, were you required to learn the alphabet? Yes. Well, if the periodic table is our alphabet, what do you need to learn? The periodic table. Okay? Do you really want to learn 118 different elements? No. Okay? I would argue that it is a bit silly to have students go through and memorize all 118. Okay? So we will only memorize 103. We're probably in the 50 to 60 range. It's still a lot. Okay? But that file, when it gets posted to Canvas, lists, I think, 50 to 60, and of those 50 to 60, I think there's 30 that are an absolute must. You have to have memorized. Where are those 30? Pretty darn close to the first 30. Okay? Why would you be expected to memorize the first and not the last ones? The first ones tend to be the most common. Comes down to what we use most frequently. Okay, there are exceptions in there. The symbol for silver was Ag, and which element is it? 47. So our number is written in the upper right-hand corner. Okay, you're required to know what silver is. Okay, but some of the other ones you won't. So it kind of skips around on which ones you need. If I'm correct, absolutely 1 through 18. And then mostly 1 through 36. There's a few in there, probably 5 or 6 that you don't need. And then it starts really jumping around. Okay? So if you open up that file, the bold ones are the ones that are super important. The non-bold ones, I was told by other faculty members students should memorize, but I don't listen to anybody. Except you, because you're asking a question. That will all be in the helpful files. Okay? It'll just be a list of the names and I think the symbols. I don't remember if the symbols are attached to them or not.
You want us to know the numbers on them too, or just the
You do not need to memorize any of the numbers. Why not? They're on the periodic table. So we don't need to worry about it.
Obviously, okay.
Yeah. So why do I have you memorize what the symbols are? Because the symbols are there.
It doesn't say.
We don't know what the symbol means. Okay? So you just need to tie the name to the symbol. We will attach numbers to them later, but not numbers that are on the periodic table, obviously. They're buried. Okay? So start working on that. Get those memorized. When are we done? Okay. Yeah, we'll just skip on. So now here's what we do, another big jump. Chapter 4. Okay? Chapter 4 is talking about models of the atom. And this is now where we kind of move in, well, really the whole first unit requires a lot of memorization. There's lots of bits and pieces that we have to nail down. I just gave you 30 to 40 elements that you have to have memorized. Right? And then we're about to talk about the model of the atom. How did we get the elements? So we look at a single piece or single smallest chunk of an element. I have the atom. Well, what makes that atom? How did we get to that point? Okay. Well, how we get there starts early 1800s with Dalton. Okay. And Dalton had an atomic theory. So he went through and looked at a variety of different mixtures of reactions and noticed that certain things held constant. And he started to come up with some rules to explain those observations. So here's a summary of his theory. Okay? An element is composed of tiny individual indestructible particles called atoms. Okay? He found that he couldn't get anything smaller than that, so he said, that's what we got. That's the smallest piece. We work with it. All atoms of an element are identical and have the same properties. So that means if I reach in and grab a carbon atom, and then reach into another pot and pull out another carbon atom, that they will have the exact same properties. No difference between them. Okay? Atoms of different elements combine to form compounds. So he's just now saying what a compound is. If I take a carbon and an oxygen, put them together, I get carbon monoxide. Okay? Death. Okay? If I take compounds, those compounds will contain those elements or atoms in small whole number ratios. Okay? So what he's saying is if I take carbon and oxygen, I can make a compound. But I could take 2 oxygens and make a new compound. I could take 3 oxygens and make a new compound. Okay? So we're looking at small numbers and then small whole numbers. That means I will never take a carbon and half of an oxygen atom. Can't happen. I can't split them. That invalidates his rule number 1. So we're looking at these small whole number ratios. We might already call into question that one, because what are we made of? Atoms. And we're combined of small ratios of atoms. How big's an atom? Really, 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 really tiny. So to make one of us, make one of me is a small number of atoms? Probably not. Relative to the whole universe, yeah, I'm probably pretty small in that respect. Okay. But we can already start to see that we run into some issues with the small amount on that. But the whole number makes sense. We can't split our atoms. And 5, atoms can combine in more than one ratio to form different compounds. We just talked about this one. Carbon with oxygen, we get carbon monoxide. Carbon with 2 oxygens, we get carbon dioxide. Okay? 2 hydrogens and an oxygen, and I get 2 hydrogens and an oxygen, and I get water. 2 hydrogens and 2 oxygens, and I get dead. Okay? There's that joke, walking into a bar, that I never can do right, so I'll just tell you, you can find it. Okay? So this is what Dalton was working with. Okay? We shift then to also look at how he processed this. If we take a look at the top there, see all those like pretty little pictures and all these circles and dots and solids and lines? That first top section, maybe you guys can see it here. Can you tell me what that says right there? Probably 20. It's going to be my guess. It says 20. 20 what? Elements. How many elements are there? Did Dalton have some issues? When Dalton was working, he was really only able to isolate and identify 20 elements. Okay? We're a little bit further ahead now. Okay? So some of his theories are going to have problems. If we take a look at what else he's got in here, what else do you think these things are? Compounds. Looking at the different combination ratios that he could get to form those different compounds. Okay? So when we move into the section of making compounds and naming compounds and organizing them, and you're complaining about formulas, just remember, if Dalton had his way, you aren't writing out letters and numbers. You're drawing circles and lines and dots and dashes and zigglies and starfish and stuff like that. Yeah, I kind of, whatever that one is, doesn't that look kind of like a starfish? Yeah. Snowflake is actually where I was going, but starfish is what came out. Right? So Dalton is just breaking things down and saying this is how we build things up. How many of his theories are actually true? To figure that out, we need to know more about our atomic understanding, or our subatomic understanding. That then has to wait to the late 1800s. So Dalton was the early 1800s. Thompson comes in at the late 1800s. Okay? And Dalton was able to discover directly 2 particles. Okay? A negatively charged particle and a positively charged particle. Okay? And he was able to prove that those could not have been elements. Okay, well, if they aren't elements and atoms, where did they come from? There has to be something that makes up our elements and atoms. Okay? There are smaller pieces than an atom. Our atoms are made up of these negative and positive particles. Okay? One of the things he was able to prove was that they had charge. Okay? So he defined the negative one to be called an electron. He defined the positive one to be called a proton. Okay? We might say, well, why didn't Dalton do this? Okay? Fascinatingly enough, this discovery hinged on one other big discovery, or invention. A vacuum. Without a vacuum, Thompson's experiment doesn't work. Because what is Thompson's experiment? He takes a glass tube, seals it up, okay, and he puts a couple electrodes on either end of it. Okay? Because we have some electric charge, but we don't know where electric charge is coming from. We just assume it's an element doing it. And with that tube, he then removes all of the air out of it. So now there's what inside it? Nothing. That's a vacuum. Removed everything. Nothing's there. And he attaches up to a really big battery and says, we're going to see a big whopping nothing. Scientists do weird stuff. Okay? And what does he see instead? It glows. Why does it glow? There's literally nothing inside this. How could it possibly glow? Something has to be moving through it. What is that something? Well, I don't know. Let's attach a battery or a magnet to it, because magnets have a polarity associated with them. What happens when he attaches the magnet to it? Whoop! The color of the glowing starts to shift, okay, either towards or away from the magnet. What does that mean about that glowing characteristic? It has a charge associated with it. And with this, he's able to now define these new particles. Why is it glowing? And this is where it gets really weird. It's not a perfect vacuum. Okay? If you just take a really big battery and hold them apart from each other, you don't really see much. Okay? When we move into a vacuum, we're now putting on so much charge that electrons are getting ejected from one side, and those electrons come flying through the air, and electrons are inherently unstable. Does anybody need proof that an electron's unstable? Okay, I need proof because I like this example. Okay? I could stick my finger in the electrical outlet. That kind of hurt. What's coming out of the electrical outlet? Electrons. That's our electrical current, is electrons. Electrons are unstable. That's why it hurts when I stick my finger in one. Okay, I don't recommend it. Don't do it. It's not pleasant. And I do know that. Okay? So what's happening is that electron is coming flying out, and there's a very small amount of other particles there. When that electron hits that other particle, it excites it. Okay? And what happens when we get excited? You get an A+ on your first exam. What are you going to do? You're just going to sit there and just be like, yeah, whatever. Okay. What if you're expecting to fail this class right now, and you get an A+ on that first exam? You're going to celebrate. How are you going to celebrate? Beer. You're just going to walk in the bar, beer. I've done that too, but.
How we order it with the appropriate chemical.
You don't want to like share with other people that you did a darn good job? Yeah. Okay. How do elements share that they just got excited? By somehow spitting out that energy. What is a form of energy? Light. They're getting excited by that electron. When they relax back down, they can release that energy as light, and that is the beam that we end up seeing. Okay? This experiment starts a cascade of tons of other experiments that result in pretty much our complete, or not complete, but our mostly complete understanding of the atom, nuclear radiation, I mean, just tons of stuff. Right? This is kind of the beginning of the era of scientific discovery and what we currently work with from this experiment. Okay? He theorized that if we have these electrons and protons, that those are going to be what makes up atoms. Okay? He didn't know how they made up atoms. He just came up with a guess. So his theory is that we have this sea of positive charge that is an element, and then electrons just sit in it, kind of float around in it. Okay? And he compared that to what he would call our plum pudding, which I think is disgusting. But plum pudding, we have some pudding, and then we got plums floating in that pudding. The plums would be our negative charge. The pudding is our sea of positive charge. And that's what he's saying an atom is. Okay, a weird fancy dessert. Okay, but that was about all he could do. So some other scientists came along to play around and manipulate this information. This one's not in your textbook. Milliken and Fletcher, okay, with some really good eyesight and patience, were actually able to calculate the exact charge on an electron. Okay, so Thompson just said it's negative. He didn't say how negative it was. Okay. Milliken and Fletcher came through and said the exact charge on an electron is 1.5924 times 10 to the minus 19 coulombs. Okay. Do we need to memorize that number or that unit? No. We just need to kind of tip our head to like that's some good work. Okay. How did that work? Okay. To figure out that charge, they have to be able to measure it. The only way that they can measure it, because electrons are so tiny, is to make larger samples and try and make single charged samples. So here's what they did. They took a big box, is a really scientific way of describing it, a little perfumery oil sprayer, and they sprayed that oil into the box. Well, what does the oil do when we spray it? It disperses, okay, into kind of a mist. Okay. That mist then does what? It falls. Okay. Eventually, it'll fall and hit the bottom of the box. But what they did is cut a small hole in the box. Okay. Because if it all falls down to where they can see it, they're going to see too much stuff. It's going to be too hard to focus on. Okay. So they put a tiny little hole so only a single drop can fall through. With that single drop, they fire a bunch of energy at it. That energy has the intent of doing what? Exciting it. Ejecting an electron. Making the drop now charged. Okay? So we now have a drop that's charged, that's falling through. They've got a microscope now aimed down this tunnel. Microscope on an oil drop. I remember, not oil, but like oil. Tiny, tiny little drop. Okay? And they're trying to focus the microscope on it. Okay? How fast is that drop going to move? Pretty fast. So that's not... and there it went. And there's the next one. Okay, so they need something to slow it down. What did we say was special about our charged particles? They can respond to our magnetic or electromagnetic fields. If the particle is now charged, what they can do is have a hand on a dial and wait for the drop to start to fall and spin the dial. And hopefully they attenuate the charge just enough on the plate that what happens to the drop? It floats. What is preventing it from falling? The charge that they can now calculate. What is causing it to fall? Gravity. Because they can now see the drop, they know the size of the drop, they know the density of the oil of the drop they put in, they can now determine the mass of the drop. They can then set up an expression to compare gravity falling down and electricity essentially causing levitation to counteract each other, and they can use that to calculate the exact charge of an electron. Nuts. You do it once, what are the odds you did it right? Remember, dial, eyeballs, for now. So how many times you got to do it? Probably thousands of times. And then averaging it. Okay? Which of them did that? Fletcher. Who gets all the... the credit for it? Milliken. Why does Milliken get all the credit? He was the professor. What was Fletcher? The student. Welcome to grad school. Okay. We'll pick up there. Sorry for running a little late.